today's session is dedicated to our teachers, the nation builders. There is a lot of misconception about computational thinking. Actually, there's a lot of difference between computer science and computational thinking. Today, through this session, we are making an effort to make it clear to you what is computational thinking, how is it important to us as a teacher and as an individual. So without delaying further, I'll hand over to Binati to proceed with today's wonderful session. And I hope you all will interact during the session and will use the chat box for sharing your questions. Over to Binati. You're on mute, Binati.
A very good evening to one and all. This workshop is being organized by Curious EduTech and the EV Experts Foundation. So before I would like to start, I would like to play a short video for you about the EV Experts Foundation. So EV Experts Foundation and Curious EduTech have come to a strategic partnership to promote computational thinking and to instantiate this in school education. So I would like to go ahead with the presentation. Let me just share my screen. Curious EduTech is an EduTech startup which is recognized with the Ministry of Corporate Affairs and recognized under the Startup India scheme. We focus to instantiate computational thinking in school to promote activity and experiment-based learning. to promote computer science as an essential skill in the school. So as a part of this initiative in India, we have partnered with the Curious EduTech. Curious EduTech has partnered with the EV Experts Foundation, and in United States, we have partnered with the Computational Thinking Alliance. So this program is being floated for both Indian citizens and US citizens. So as a part of this, we conduct workshops and courses for students on computational thinking, programming, and we also organize professional development for school teachers. So let us start with by addressing a few misconceptions and themes we consistently hear from our students. So before that, I would like all the participants to take up a pre-workshop survey. So I'm sharing the link to you in the chat box. It would take 2 minutes. So I request all the participants to fill up this pre-workshop survey. So, sorry, this is the Meet link. I'm sharing you the form. So this will help us give a background of the understanding of all the participants, like what do you understand about computational thinking. So it will be helpful for us to go ahead with the workshop. So I request all the participants to fill up this form. It would take hardly 2 minutes. There are 10 questions with yes or no answers. So I request all of them to fill out this form. So it's 4:12. I'll wait 2 minutes, 2 to 3 minutes. We can start the presentation at 4:15 again. So let me know if you're having any issues filling up this form. So I request all the participants to please fill up the pre-workshop survey form. We have around 67 participants. I would encourage you to fill up this form. It would give us an understanding of the foundation or the generic idea of what understanding you have on computational thinking.
Good afternoon, ma'am.
Yes.
Ma'am, I'm using a phone right now and I can't see that form. So where exactly do I find that form?
So you have a chat. Can you see the chat?
No, ma'am, I can't see it today.
In your form, in your phone, if you have joined Google Meet in your phone, towards the end you'll be having a 3 dots on the top right.
Yes, ma'am. I've clicked on that.
Yeah, you see a chat option. If you click on the chat, you have the form in the chat box.
Okay, ma'am. Oh, okay, ma'am, I got it. Thank you.
Yeah. So we have received around 28 responses. So maybe I'll wait for another minute. We encourage active participation of all the participants.
Excuse me, ma'am.
Yes, yes.
Ma'am, actually in the subjects we have the subjects not of the commerce stream, like I teach accountancy and business studies. So what should I fill there?
So you can actually select social sciences. Yeah. On 43 responses. So the remaining, I request you to fill up the form. Meanwhile, I'll just go so that we don't lose on time. So I have got a basic understanding based on the 43 responses of what the understanding of computational thinking or computer science is. So I'll go ahead with the presentation. Thank you so much. I appreciate you all for filling up the form. Yes. So let us address some misconceptions and themes we consistently hear from our advocacy for students across the country. So the first one is that we should be teaching our kids. So is the screen visible?
Yes, we can see.
Yes, ma'am.
Okay, great. So the first one is that we should be teaching our kids to code. So how many of you agree? So you can raise your hands, those who agree. So from the form that you have filled up, I see that 75% of you say that our students should learn to code. But the truth is that our school should teach computer science. So how is this different? Our view is that schools should be teaching computer science. Coding is an important tool for computer science, but it is like arithmetic is for mathematics and words are a tool for English. So similarly, coding is a tool for computer science, and computer science is something very different and is huge than coding. So coding creates software, but computer science is a broad field encompassing deep concepts that go well beyond coding. And all students should have access to computer science courses in their schools. So the other misconception is that there's a temptation to think that it is only the IT industry, the tech industry, that is desperately trying to hire computer programmers in India. So I am very happy to see that everybody, almost everyone, 90% of the teachers in your school believe that it's a myth. So yes, I agree with you all. Every industry is desperately trying to hire computer programmers, not only in India, everywhere. It's not just IBM, Google, Twitter, Microsoft, Facebook who are participating in this new opportunity, but every industry is participating in this new opportunity. So computers and software are changing everything. So computer programmers are needed in every industry across the country. So can you imagine in 2030, 10 years from now, what will a career look like? So it will be a workforce that will be very data-driven, that leverages technology to bring new ideas into marketplace. So employers will need workers that understand not only how to use technology, but how to create and manipulate. So we need producers, not consumers. Just being facile with the technology will not be enough. So our students will need to be innovators and creators. And to do this, they need to learn the opportunities. They need to learn computer science. So it's computer science is just not about learning technology, but it is about logic, problem solving, and creativity. So the reality is that computer science is about all of these things. It teaches students how to think differently about problems they are trying to solve in any context. It teaches kids how to create digital artifacts, how those artifacts impact the world around them by looking at issues such as privacy and security. For example, if you look at the face lock or the finger lock on your phone, so that's a software that is being created, and you can see how that software is impacting the security of your phone. How are you able to secure your laptops and phones using that? So the students must know the opportunities, must know where to innovate and what is the impact of their innovation. A very simple way to think about this is computer science teaches kids how to create new technologies instead of just being consumers of technology. So we can do better than simply teaching literacy, computer literacy or technology literacy to the students. We can make kids creators of the technology. So technology affects every field. You can see that the reality is that the technology affects not only commerce or healthcare, but it affects each and every area in space, in our homes, on our roads. So you can see the automatic cars without drivers. You can see the phones which measure the insulin level in our body. And in space and in our homes, we are automating everything like the heating system, the door unlock, you're putting your fingerprint and the door is getting unlocked. The lights are turning on by detecting your presence. So everything is being automated and technology is affecting every field. So the technology requirements after 10 years would be different. Who would have thought, like in 2000, in the beginning of this decade, 2 decades ago, in the beginning of this millennium in 2000, nobody might have thought that phones would become so common. Phones would become the devices they would be the medium for us to connect to the internet. Now phones are everywhere and internet is accessible to everyone. Similarly, the technology requirements after 10 years would be different. The question is, how can we train our students to be diverse, creative producers of such technology? How can we adapt them through the school education that we are giving 10 years prior to that technology being created? The answer is computational thinking. So computational thinking is a thought process to formulate problems and solutions in a way that humans or computers can understand. So it is something bigger than computer science. It is something bigger than coding that can be applied to all fields. Computational thinking is a combination of 4 major techniques: problem decomposition, abstraction, algorithmic thinking, pattern recognition. So if you have any questions, participants, please feel free to drop it in the chat box. We'll discuss your questions at the end of the session. So problem decomposition, it helps you to divide larger problems into smaller problems and solve one problem each at a time until you solve all the problems. Abstraction helps you pull out important details, see or generalize relationship of these details to other situations. For example, in a history class, you might explain about the greatest leaders in the history, and you might ask students to abstract the good qualities in those leaders. So that is how you can integrate computational thinkings, and you can help students practice these techniques and bring out the useful solution out of it through such techniques and activities. So pattern recognition, this is the third technique. It helps you to identify a pattern and observe the possibilities to generalize and devise a solution. Algorithmic thinking is a step-by-step procedure to solve problems. It's not just a simple recipe. It's like you have a procedure, and how can you implement step by step to solve a small problem and then solve each problem. So all these techniques are integrated together. In algorithmic thinking, the important question to ask is, so given a problem, is this problem solvable? How exact must the result be to be good enough? What are the steps that we need to take to achieve a good result? So computational thinking is a success skill. So all these techniques integrated together will help you formulate any problem and devise any solution to it. So once you master this technique, you are the best at your workplace or in the place where you go to work or attend an interview or being a student. You can solve any problem throughout your life once you master this technique. So I'll start with the problem. So this is a problem. So I hope everybody can see you have to add numbers from 1 to 200. So the trick here is you will not use any calculator. Okay. And you have to add these numbers within 30 seconds. So once I start the timer, there will be a blue bar that will appear at the right corner of the screen. And once it reaches the vertical line, your time is up. So whoever comes up with the answer can give me the answer in the chat box. So Any questions till now about this challenge? Any questions? No. So, okay. So, I'm starting your timer. So, whoever has the answer, please write it in the chat box. Your time starts now. So, no using any formula. So, assume that this is a task for a 5th grade student and who doesn't know the formula. So, how are you going to come up with this? Okay, I see answers coming up. And meanwhile, teachers who haven't filled the pre-workshop survey form, I request you to kindly respond to the survey form, because I see 51 responses and there are approximately 72 staff members who have joined the meeting. I request the staff members to please take the pre-workshop survey. I would post the link once again here. Okay, so I think your time is up. So the 30 seconds are over, and so yes, congratulations to the teachers who have come up with the right answer. So yes, the answer, as most of you have mentioned, it's 20,100 is the right answer. I think some of the teachers have got the answer right. So how do you actually compute? I mean, think from the perspective of a 5th grader. So one who doesn't know the formula, how is he going to compute this sum? So let's do this thing. So this is a problem that we are having at our hand. So first, what we need to do, let's abstract what we need to do. What we need to do is add, right? Add natural numbers. Second, we have a problem of adding from 1 to 200. So let's do problem decomposition. Let's divide this larger problem into smaller problems. Smaller problems which we can solve. Okay, so let's add 1 and 200. So this is 201, and then we had 2, 199. This is 201. So we are dividing into smaller problems. So I would like to ask, do you see any pattern? Please, the teachers can answer if you can see any pattern here. Please feel free to answer. It's a discussion. So does any of the participants see a pattern?
There will be 100. If you go from front and back.
Exactly.
100.
Correct. So you see a pattern that every sum is giving a number 201. And when you generalize this pattern, you see that there are 100 such pairs. So now you apply your algorithmic thinking where you do a summation of this to give you the total value. So you don't need any formula, you don't need any calculator. So I am sure that all of you will require less than 30 seconds to do this if you would be applying computational thinking. So this is how you can bring computational thinking into practice. This is how you can integrate it with other subjects. So this is an example. after 10 years, when the technology is different from today, when the problems, when our students have to face problems which are unseen today, this is the skill which can assist them in facing those problems and devising solutions to those problems. So the problems could be anything ranging from climate crisis to sustainable energy. So all of such kind of things can be solved using these 4 techniques. So what exactly is computational thinking now? Anybody would like to give me inputs from the audience? Teachers, please feel free to give in inputs. So what do you think computational thinking is? Do you think it's a problem-solving skill?
And it can be interpreted as a logical reasoning or a logical interpretation of a question.
Okay, good. And
this is a way of breaking down complex problem into smaller problems, and which will help us to ultimately solve the entire thing.
yes, perfect. And more answers? Any more answers? So how many of you think that computational thinking can be applied to any sort of problems? Would you agree?
Yes, ma'am.
Okay, so computational thinking is logic, it's problem-solving process. So combining all of them together, you can say computational thinking is a thought process. So it will help us identify how difficult a problem is, how a problem can be solved, how technology can be applied to that problem. So I'll give you an analogy. Like when you are, when you want to solve any problem, when you want to develop a software for a given problem. So for example, you have a calculator. Okay, so you want to build a software version of this calculator. So using abstraction, you can devise what are the things that are required for a calculator. You need buttons, you need numbers, you need a screen to display input output, you need operators, right? So then you use problem decomposition to find out all of these things, what are required. Then you use algorithmic thinking, step-by-step procedure. You draw a flow chart. Okay, first I give an input. Then I see the operator, which operator I have. And if it's an addition, then I perform sum of the 2 numbers that are given as input. So you create a logical flowchart and then you apply a programming language onto it. So it's just like if you are going for an elocution and suppose you have to speak on Sundarbans. Okay, so how the climate change is affecting the mangroves in Sundarbans. So to speak on that topic, you first need to have some idea. Okay, I need to speak on this point, this point, this point. And then you can articulate your speech. So developing software is just like that. You have a strategy for your solution and then you just apply the programming language onto it. So how technology can be applied onto the problem? What computational strategies can you employ? And what is the power and limit of human and computer intelligence is? So this is what computational thinking is about. So now let's see what it's not. So we have seen what computational thinking is. Now let's also see what it's not. So it's not just technical details for using software. It's not thinking like a computer. It's not programming because computers actually don't think. I mean, you can consider them to be dumb. Whatever instructions you're giving to them, they are going to execute it. So, and it's not necessarily programming. And it doesn't always require a computer. So you might be adopting different learning strategies to teach. So how is this different from other learning strategies? It's not procedural, it's not constructionist, it's not just integrated. So now I would like to give you a few examples of how you can apply computational thinking to different subjects. So how many arts teachers are there? Can you raise your hands? How many arts teachers do we have? So you can put in chat. Yeah, 1. Okay, 2. So I have 2 arts teachers here along with me, 3. So the number is going up. That's nice. So when you are painting a portrait, so some students are natural painters. They have the ability within them. For some it's difficult to adopt. So how do you give the student pointers, like the best way, or how do you say that, okay, you don't know how to paint, so how do you teach the student? Can you just give me some inputs, maybe? Any of the teachers? So suppose if they are doing a painting of Leonardo da Vinci, who's on the slide, and they are stuck at some point near the nose or the eyes. So how do you guide the student? Or maybe you can use computational thinking here, maybe. So any answers? Okay, I'll go ahead then. So maybe you can use a grid. So you can divide the painting into grid, and then it's actually problem decomposition. So the problem of painting one whole image has been decomposed now to draw a particular segment of the image at one particular point of time. So at a given point of time, the student has to worry only to paint this particular portion. So painting each segment at one particular point of time will allow the student to complete the painting. How many of you would agree? So you don't want to speak? You can put it in the chat, not a problem. So would you agree? Okay. So computational thinking can also be used for digital art. So suppose you have gone to a beach and you have seen some scenery like this, and you would like to, one way to do is paint it using crayons and paints, oil paints. That's wonderful. And the other way is you can also create a digital art. So you can use abstraction, like what are the things that you have seen? What are the things? And then you can visualize and list out the things that you have seen, and then do a problem decomposition. Okay, I have to create the moon. I have to create the background. I have to create a sea. And then I have to create the shadow, and then the stars. So you have 5 sub-problems, and then you create each one step by step. So you have the solution. Now the only thing that you have to do is map it onto technology. Computational thinking can be used to express yourself. So you can create a website for a social cause or for some problem that is prevailing in your particular location. How do you apply it to geography? So there might be, I assume there are social science teachers here. So how do we integrate computational thinking with geography? The students can be given an opportunity to practice computational thinking techniques by supplementing the lesson with an activity. For example, in a geography class, when we are teaching types of forest, an activity to analyze the relationship between the forest and the ice cap would help students to analyze the relation between the forest and the climate changes. So it will help them analyze the importance of forests. And at the same time, it will help them in practicing the skills like opposing standpoint, abstraction, and pattern recognition. You may also include several ICT resources and open source resources to create such activities. So you can use computational thinking to introduce the lesson, and this is how you can integrate it in a geography lesson. Another example, in an environmental science class, when you are having a lesson on climate change. So climate change is a topic of concern for all of us. When teaching this as a part of environmental science, one can inculcate computational thinking to do a case study. Theoretically, you can teach them on carbon emissions, their causes, their reasons for emission and their effects. The other way is you can ask them to do a case study on themselves and their respective families. So you can ask them, like, what is their footprint? What is the ecological footprint of their family? You can redirect them to ecological footprint calculator and help them understand how much they contribute to the climate change. What are the day-to-day activities they can perform, or what are the changes that are to be done to their lifestyle that will reduce their ecological footprint and will make our earth self-sufficient. So teaching theoretically is important, but at the same time, making the students understand the importance of what they are learning, understand the prevalent situation and devise a solution to that situation will help them in becoming diverse solution producers. And it will at the same time also make learning interesting for them. So such kind of activity and integrating computational thinking in lesson will shift the face of learning from just learning mere facts to understanding the root cause and finding the solution. So how do you include computational thinking in sports? So sports is an integral part of the curriculum. It's a core activity. So when a student plays a game, so for example, if you take badminton, so I think everyone recognizes badminton player Saina Nehwal, right? So how do you build your game? How do you try to win in your game? How do you try to put maximum effort? So you can maximize your effort by first analyzing your opponent's game, introspect your own game. You make abstraction by looking at a game. So you abstract what are the strengths and the weakness of opponents and your own strength and weakness, and then devise a strategy for your game. So computational thinking would be useful not only in single player games, but in multiplayer games as well. So this is the interesting part. How many computer science teachers are there? So any computer science teachers? I see in the chat. Okay. So any computer science teachers, can you please let me know, do you teach Python programming or any programming in the school?
Yes, ma'am.
Okay.
We are currently teaching Python.
Wonderful, wonderful. So suppose if there are functions, so there are functions in Python. So how do you teach functions to the student?
As I said, in the definition, while defining the concept of this computational thinking, like breaking the entire problem into small modules. So in that case, ma'am, it will be easy for them to learn how we can go for one particular task at a time with the help of one specific module, and first we'll finish that job and we'll proceed to the other one.
Wonderful.
So yeah, that's the way.
So for functions, how do you go? I mean, so you say, okay, this is how we define the function, and so you need something, you go back and execute that. So
we give some realistic examples also sometimes, yeah.
Okay, perfect, perfect. So I'll give you one example, okay? Okay, I am sharing the screen. One second, let me just share the screen. Okay, so the screen is visible, right?
Yes.
So when you're learning functions and parameters, so let me give you an example. So how many of you know this song? Old MacDonald had a farm, E-I-E-I-O. So I think we must have learned this song when we are a child, right? So in kindergarten, in most of the schools, they teach this kind of poems to students or common songs to students. So here you tell the student, okay, we have a song. I don't want to write the song again and again. So I define a song, and here I mention that there is an animal in the farm and it makes a sound. So this is an animal and a sound. So this is the song. So I have the first stanza here as chorus, cow and moo. So you just replace the animal with cow and then replace the sound with move. So you get the first para of the song. Old MacDonald had a farm, E-I-E-I-O, and on his farm he had a cow, E-I-E-I-O, with a moo here and a moo there, right? So that's the first para. And then the second para, you have again. So, and on his farm he had a duck with a quack quack here and a quack quack there. And then for the third para, you have chickens and cluck. So I don't want to write this song. I tell the computer that this is the song, and wherever you find animal, you just replace with cow and move. And then when I call you again, then replace with duck and quack. When I call you again, replace with chickens and cluck. So I don't do the work. You do all the work. I just give you the parameters. So this is called a function. So you define the work that has to be done somewhere in a module which is called as function, and then whatever values that you give to the function, those you call as parameters. So do you agree that this is simpler to understand?
But ma'am, if we go into the detail of this particular example, I think this is the constructor part. Like if you know Python programming, like in programming also we have this concept where we change the parameter and we keep the name same as the class.
Yes.
So that way we can, I think, explain the constructor with this example.
Yes.
But by defining multiple functions, ma'am, I don't think it will be helpful, because here we are using the same function name, that is chorus.
Yes. So this is
only the parameters are different.
Just to give you a small example of how we can, use pattern recognition to teach.
Okay.
So this is an example where I was trying to show you how we can use computational thinking in teaching computer science. So for students, to introduce students with computer science, so rather than just directly going on to the syntax, we can give them such examples. So yes, for constructive functions, we can give this example. For other functions with different functions, we can give a different example. So I agree with you, sir. And this is, I just wanted to show how one of the techniques, pattern recognition, can be used to teach students computer science. So general science, for example, if you're teaching a topic which is called as insulation or regarding insulators, so you can ask students, which is a good insulator? So you tell them, like, what is insulation, what is insulator, what are its uses, why is it used for? And then when you ask students such kind of questions, what is a good insulator, that will help students produce a possibility of range of answers. So that will allow them to think. So in mathematics, for example, if you are adding to unlike fractions, something like this, 13 by 12 plus 4 by 15. So when you need to add unlike fractions, so for a grade 2 student, for example, or grade 2 or 3. So when he has to add, so one way is to tell them, like, okay, you have to find the least common multiple, you find the LCM, find a common denominator, and then multiply with the numerator and then add it, and then you get the sum. So that's one way. The second way is, okay, so what do you know? What do you know about adding fractions? So you know to add like fractions. It is simpler to add like fractions because they are having the same denominator. Right? So this is what you already know, and this is what you have learned. So now you are having unlike fractions. So let's decompose this problem into two things. Convert to like fractions. So you convert these unlike fractions to like fractions. This is your first problem. And then you add these like fractions. That's your second problem. So wouldn't such kind of thinking make things easy for the student? So not only like adding unlike fractions, it would give them a scope of learning. I mean, a scope where they can think that, okay, even if I don't know anything, even if I see something which is new, I can go back and look onto what I already know. How can I convert this thing into something which I already know? Or how can I apply the technique that I have already know onto this? And you can also use tools like Scratch to teach mathematics. So every 21st century student should have a chance to learn about computational thinking, algorithms, how to make apps, and how the internet works. So let's take a little audience mock quiz. I mean, how many of you can answer these questions? What is photosynthesis? You can type your answer in the chat box. So what is photosynthesis, or what is H2O? So what is photosynthesis or H2O? Maybe you can answer what is H2O. So I'll type in what is H2O. No answer? What is, yeah, H2O is water. Water, yeah. So H2O is water, right? Yeah, very good. So these are the things that we expect school-going students to know, right? So every 21st century student should also have a chance to learn about algorithms, how to make an app, or how the internet works. Right now, there's no expectation in our schools that students will even have a basic understanding of these concepts, even though they are driving a larger part of our society. So it's equally important for the students to understand what a for loop is and how it is used, and how to design algorithms. Is as it is, they understand how to solve equation or how plants live. So it's equally important. The main reason that computational thinking is now foundational knowledge is because it allows students to think about problems differently. Students will gain computational thinking skills which embody a more robust way to think about problems, and the problem-solving process can be applied to any field of study and to any problem. So if you're facing a big, ambiguous project at home or work, computational thinking and problem-solving process can help you break this problem into smaller chunks. Recognizing what's important and what needs to be solved first are critical thinking skills that are valuable in any context. Even our new national education policy, which is floated in 2020, recommends that quantitative and logical reasoning, computational thinking, be a part of classroom curriculum. So they expect the classrooms to be interactive and fun classrooms. So the computational thinking, as I've mentioned in the previous slides, that we necessarily need not have a computer. It necessarily need not be programming. It could also be worksheet based. It could be activity based. So they also recommend computational thinking to be taught through hands-on assessments and worksheets. And computational thinking is going to be a part of the board examinations. They are going to restructure our board examinations to include one exam in digital literacy or in computational thinking. From age 6 onwards, it is recommended that computational thinking be integrated into the school curriculum and to be taught effectively with well-designed paper worksheets. So, how much does an average computer cost? What do you think an average computer costs? Yeah. Any answers? How much does an average computer cost? I hope some of you are connected with the laptops, right? Yeah, 20 to 25,000, 35,000, 20,000. Yeah. So yes, on an average, if you think that the computer costs around 25,000, so after 30 years, so 10 years ago, the computer must have costed drastically different from 25,000. It must have costed a fortune, like 50,000 or more than a lakh, if you take a decade back. Similarly, after 3 decades, maybe for the same amount, we might get a supercomputer, which is of high performance and which has the capability of intelligence of the entire human race. So to give instructions to such a computer and to make efficient use of resources, our students must be capable to formulate the problem and devise a strategy that such computers can execute. So you have the computing resources, but you must be capable to make efficient and 100% usage of those resources. So for such kind of capabilities, you need computational thinking. this is where your CT skills come in. So we float computational thinking courses for students of different ages. So before I go into these details, if there are any questions, please let me know. I'm open to questions. So if there are any questions, anything you would like to ask. Any questions? So if there are no questions, I would like to give you a post-workshop survey form. So it's the same kind of survey form. I would like to see what kind of impact the workshop is having on you. So I am putting the link in the chat. So it would be very kind of you. You could fill up the post workshop survey form. Meanwhile, I would explain you about our different courses that we offer for the students to float computational thinking among students. So please fill this form while I go through the courses. Okay, I'll be sharing the screen. So these are the different courses that we float for the students. So we start floating computational thinking courses from age 8 onwards. So the first course that we have is computational thinking for computational thinking 1, which is for age 8. In this, we teach students different aspects of computational thinking. And these are the number of sessions that we have for students. Each session is of 1 hour. It's a worksheet-based model. So we send out the worksheets to the students, and it's an online course. So the second is for the age group 9. So it's computational thinking 2. It's applying computational thinking to different real life problems. So we give students with problems like finding the shortest distance from their home to the school. So a map is given to them and the real distance is given to them, and how they can compute the shortest distance, the shortest path using by applying different kinds of algorithms or different computational techniques, how they can devise a solution. So that's an example that I've given from the worksheets that we'll be providing them. So this is computational thinking 2, and we have computer science principles. So in this, we'll be teaching introduction to computers, email, hardware. How do you include diversity and equity in computer science? So this is not a course something like we give them a definition, examples, or show them a video. It's all activity based. So we give students, we make students, like when you are explaining about the internet, like each student plays a role of a computer, and then how they communicate. How is a network of computers called internet? So we give them examples, and through live demonstration, through activities, this is how we teach students. Then we have for age group of 10 or grade 6, we have computational thinking 3, wherein we have understanding computer science through computational thinking. In this course, we teach students about the broader aspect of computational thinking, computer science. So we tell them, like, we explain them how computer science is not just about coding, how it's about logic, problem solving, creativity, what is data, algorithms, computer networks, security. So all these aspects come under computer science, understanding computer science through computational thinking. And for age 11, here we have the visual programming part, which is we use Scratch to make them understand programming concepts, like the example that I've given to you. How do we teach about functions? So that's a small example. So we use such kind of examples to teach them programming concepts through activities, and then implement that particular concept on a visual programming platform like Scratch. And we through that process, we help them in creating games, and like games and animations and stories. Or sometimes we also give students a project wherein, they, for example, after teaching Scratch, we ask them like, okay, you have this problem. So what are the different problems that you're facing in your locality? So how would you like to create a video for that particular problem on Scratch? So first we'll ask them to demonstrate how they are going to formulate that problem using computational thinking, and then how they're going to do it on Scratch. So this gives them, it gives an immense impact on the student, and the video also shows what is the level of understanding that the student has gained. What is the impact on the student? How well is he practicing the computational thinking techniques? For age 12, we have Python programming. So application-based Python programming. So we would be teaching the concepts to the students, as I've explained you previously, and we will be teaching them applied programming. Unlike teaching them like, okay, this is the Python syntax and this is how you use it. What we do is we give them examples, like as I've given you a previous example about the calculator. So given a calculator, what do you abstract? How do you do a problem decomposition? How do you develop a flow chart to create a calculator? And then what are the Python programming concepts that you required to create a software version of this? So that's how they are going to learn Python programming. And so simultaneously, they are going to learn the syntax. At the same time, they're also going to learn how do they apply it. So unlike the other programs that are available in the market, where they say that, okay, you are going to learn web designing in a month. So there, what happens usually is the students design something, but there are already inbuilt functions. So they mostly use drag and drop, and the student is clueless, like, what is a function? I know it's a black box. So when I need to call something, when I need to draw something, I simply call the draw function. But what is there inside the draw function is not known. It's a black box to the student. So we don't do that. So we give them an example. We go step by step. We solve each of them, draw a flow chart, make the student formulate it, and then convert it into Python. So as a part of it, we do the GUI programming, game designing, and animations. And then we also have a web designing course. And then we have computer science principles too. It's a project-based course, and we have data visualization analysis, creating media, audiovisual representations. For grade 9, we have artificial intelligence and how we can apply computational thinking and design thinking in developing AI applications, machine learning applications, and we introduce them to natural language processing and computer vision. So it's important for our students to learn computer science, programming in the same way that they are going to learn maths and physics if they have to sustain in this 21st century. It's not just in India that we have started with programming. So if you look at countries like USA and UK, they have started teaching coding from grade 3 and grade 2. So they don't use computers there. They use computational thinking to teach programming. So once they have strong foundation, when they move a grade up, when they come to middle school, they start coding. And we also have CS Principles 3, wherein for grade 9, wherein we have digital information, internet, data, cybersecurity, and global impacts. So this is a broad range of courses that we are offering for the students. So we would be delighted to offer these courses for your school as well. So it's now in our hands to make our students curious learners, knowledgeable, critical thinkers with reasoning and problem-solving skills. So if there are any questions, I would be more than happy to answer. And you can always contact us on these phone numbers, or you can email me or Nidhi. These are our email address. So you can make a note of these, and these would also be shared to you. Please feel free to contact us on these numbers if you have any queries or for any further discussion. So any queries? Any questions? So the post-workshop survey, I have received around 33 responses. I would request you to please submit the response for the post-workshop. So I'm sharing you the link once again. Yes, the form has similar questions. So please don't think it's... So we would like to see the impact by comparing the answers for the pre and the post-workshop. So I have reshaped the link once again.
Good afternoon, ma'am.
Yes.
Actually, I would like to place like a mother. My child is 12 years old. So like if I'm interested with the course, can she go with the course which is for the 12 years children? Because basically she has not done any other courses except whatever she's doing in the school. So will she be able to do the course which is applicable to 12 years old child?
Okay, so which course would you like for your child? I mean, the 12 years, for
Yes.
12 years, we have Python programming and Python Android, Python web designing and data
Yes.
and science principles. Yes, she can go for the applied Python programming course. So yes, definitely she can do that. So if she wants to gain an understanding of computational thinking, then she can definitely take up any of the computational thinking courses. So if she even does not understand what computational thinking is, when she goes for the Python programming course, yes, we will be having an introductory session for computational thinking for those who are not familiar with computational thinking.
Okay, ma'am. Like, will the session be in groups or it will be in a individual session? Like, I would like to know that also.
Okay, so when we so it's all about when you say group or individual, it depends like on pricing. So if it's for individual students, definitely the pricing would be on a higher end. So usually we do it in groups of 5 to 10 students for individual participants. But if you're doing it for schools, then we would do it based on the requirement of the school management.
Okay. No, actually what I feel is that computer is certain subjects where the child has to be involved, presenting herself also, the examples and all, rather just be listening. So that was my concern. Okay.
Yes. And computer science reiterates things. I mean, what you're learning in other subjects, it helps you build the logic and it makes your foundation strong for other subjects. That's for sure.
You know, actually it is a practical based subject. So will it be possible to learn online?
Yes, definitely. We have already done it for several schools and we are floating it in the United States also. So yes, absolutely.
Okay. Thank you, ma'am. Would be loving to waiting for your course. Thank you, ma'am.
So any further questions? Okay, so can you all maybe turn on the video so that we can have a selfie? Jayashri ma'am, yeah, I request all the participants. Thank you so much. So Sadhna, will it be possible to take a snapshot? So just 1 second, I would. Thank you so much. Nidhi, I would hand over it to you. Nidhi, you're muted. You're muted.
Yeah, thank you, Vinati, for this lovely session. And thank you, everyone, for spending 1 hour of this evening with us. It was lovely being with you. And a lot of thanks to Jayashree ma'am for giving us this opportunity to conduct this workshop for her staff members. As Vinati has already shared the details about the courses, these can be considered from a parent's point of view or a school point of view. So it depends upon the school management. If the school management is interested, then we can have a discussion for the collective course for all the students. Otherwise, if as a parent, as a guardian, or a relative, you want to recommend this course for a child or for somebody you know, you can always contact us. Thank you once again. Thank you for being with us. Bye.
Thank you, ma'am.